Hello everyone, this is Xiaoming Gu, a PhD student from National University of Singapore. I'm glad to share our ACM multimedia paper, MMALT, a multimodal automatic lyric transcription system. In this research, we are attempting to solve a task named as automatic lyric transcription, which refers to transcribing the lyrics from audio recordings of singing. However, this task is not trivial in the real applications compared to its counterpart task, automatic speech recognition. Let's imagine that you are at a concert. The singer is standing at the stage, singing a song while playing the guitar. We intended to transcribe the lyrics what he's singing. However, there are many perturbations, such as the musical accompaniments, the applause and cheers from the audience, and also maybe the environmental noise, which is also encountered in ASR tasks. Therefore, to tackle this problem, the natural way is to introduce a multimodal practice. Firstly, it can be expected that when one modality fails to complete the task due to the perturbations, other modalities can still play a part in the recognition task. Secondly, from the literature, we have witnessed the widely empirical success of multimodal practice. Therefore, we propose our problem setting as well as our solutions. Our problem setting is named as multimodal automatic lyric transcription. The input includes audio signal, which records the singing voice, the video signal, which records the lip movements, as well as the MU signal. The output is the text, which is a lyric transcription. To understand better about these modalities, I will firstly explain how we curate our dataset since there are no existing multimodal ALT datasets. There are 3 steps in the dataset curation. Firstly, we choose the same 20 songs as published research dataset named NUS48E. There are English songs with wide phonemic coverage, ease of learning, and high variation in genre and tempo. Then we ask the participants to sing the songs. Meanwhile, we use devices to collect the data. We used a condenser microphone to record the singing voice. We used a video camera to capture the singer's lip movements. In addition to the 2 most widely used modalities, we also managed to record the motion data of singers. This was achieved by a device named eSense, earbuds equipped with MU sensors, which is able to capture the movements of singer's head and jaws. They are related to the pronunciations during the singing empirically. After the data collection, we annotated the dataset in utterance level and then segmented the data according to the annotations. For the processing of videos, the regions around the lip area, which is our regions of interest, were cropped from the original video. We divide the dataset into train, validation, and test splits so that different splits contain recordings of different songs. Here are the statistics of our N20EM dataset. After you have the idea of where our modalities come from, I will introduce our MMALT system, which is the core of this presentation. As shown in this figure, our MMALT system includes 2 main parts, which I will introduce in detail. The objective of feature representation learning front-end is to perform representation learning. Since we have 3 modalities, how to represent each modality as well as combining all modalities together is a key issue here. Therefore, we design modality-specific encoders to learn representations from a single modality and a feature fusion module to learn composite representations. For autoencoder, we propose to adopt the Wave2Vec2, which is a popular pre-trained model on automatic speech recognition task. To retain its learned knowledge from speech data, we adopt the transfer learning strategy. Here we just provide some basic knowledge about Wave2Vec2. The structure of Wave2Vec2 consists of a CNN and a transformer. The input is a raw waveform. Wave2Vec2 is trained through 2 stages, pre-training and fine-tuning. To retain the knowledge from speech data, we initialize our audio encoder by Wave2Vec2, which has been pre-trained and fine-tuned instead of random initialization. For video encoder, we propose to adopt AV-Hubert, which is a pre-trained model for lip reading, and we use a similar transfer learning strategy. The input to AV-Hubert is videos of lip movements. AV-Hubert includes a Resonate 18 and a transformer. We initialize the learnable weights of video encoder through the similar way as audio encoder. We adopt a CRNN as the IMU encoder for the feature extraction of IMU signals. This network is more lightweight compared to audio and video encoders. Here's the structure of the IMU encoder. The most important components are a series of one-dimensional convolutional layers and bidirectional GRU layers. After we obtain the modality-specific representations from the input, now we need to explore the complementary relationship and redundancy of different modalities. To achieve this objective, we design our feature fusion modules. As shown in the right picture, we firstly align the time resolutions and feature dimensions of different modalities since they are processed by different encoders. After that, we propose a residual cross-attention module to fuse the features. The residual cross-attention is constructed based on transformer block. The difference is that we add multi-head cross-attention as a residual shortcut to original multi-head self-attention. The motivation behind this idea is to delve into the missing relationship between frames that are not attended when using only self-attention. Here we also visualize the attention maps of self-attention and cross-attention. The first one is self-attention and the other ones are cross-attention. We can notice that these three attention maps have extracted the similar patterns. However, the cross-attention maps show some missing relationship between frames which self-attention fails to recognize, which validates the effectiveness of our RCA design. After explaining our feature representation learning front end, now we turn to automatic lip transcription backend. Its objective is to transform the learned features into task-specific outputs, in this case, the lyrics. The backend consists of a hybrid CTC attention backend and a language model. Here, the language model is used to eliminate the implausible predictions. The design of hybrid CTC attention backend benefits from both the CTC systems and S2S systems, which are two mainstream practice in ASR and ALT tasks. The hybrid CTC attention backend adopts an encoder-decoder fashion. We use an MLP to further encode the fused features before fed into the decoder. There are two branches in the decoder. One branch outputs the CTC prediction and another branch outputs the sequence-to-sequence prediction. What is worthy of attention is that we adopt the character-level tokenizers. Now we have known how our MMLT is built. The next step is to train the whole system. Firstly, language model is trained separately on corpus of lyrics. The other model parts are trained on our curated dataset N20EM through both the CTC loss and S2S loss. We introduce a hyperparameter to balance two loss terms. After training the MMALT, we can use it to make the inference. In this stage, we compute the probability of lyric candidates based on CTC S2S prediction, as well as language model. Here I show the optimization objective. We introduce two hyperparameters to balance these three terms. The most likely lyrics will be found via beam search. To evaluate our proposed MMALT system, we conducted both single model experiments and multimodal experiments. The single model experiments are designed to evaluate the representation learning of modality-specific encoders, The multimodal experiments are designed to evaluate the performance of MMALT system on both clean and noisy scenarios. Traditionally, the TDNN network and its variants dominate the field of ALT. This is the first attempt to transfer the pre-trained model from speech domain into the singing domain. Therefore, we need to evaluate its effectiveness. To deal with this problem, we choose DSync dataset, which is one of the largest benchmark singing datasets to train and evaluate our autoencoder. The performance metric is word error rate. As shown in this table, compared to TDN networks, our audio encoder can exceed the performance of previous approaches, which validates that Wave2Vec2 together with transfer learning enables a strong audio encoder. Then we train the Wave2Vec2 on our M20EM dataset with only audio input to build the baseline for this new dataset. The performance is tested on M20EM. Furthermore, we also find that training the model on both M20EM and DSync dataset demonstrates better empirical performance. Since there is no benchmark datasets for video-only ALT, we firstly initialize this task and name it as lyric lip reading. Thanks to the curation of M20EM dataset, we build the first baseline using our video encoder. As shown in this table, we can conclude that CTC S2S as well as language model contributes to the best performance we can achieve. In our preliminary experiments, we noticed that it is difficult to transcribe the lyrics from only MU signal. We assume that the MU signal is not as informative as audio and video, when the goal is to predict words. Therefore, we attempt to let it solve a task that is relevant to ALT, but with lower difficulty, which is voice activity detection through MU signals. Here we show the performance of a MU encoder on the VAD task, which achieves F-score of more than 82%. To further show the relationship between MU and ALT task, we plot the figure to compare the VAD prediction and audio signal. As shown here, the MU encoder outputs higher values when the audio has activation, and lower values when the audio is silenced. It can be concluded that MU is capable to hint the system when the voice is being produced and when it is not. Therefore, MU encoder provide additional meaningful inductive bias for consequent training of the whole ALT system. Now, through our single model experiments, we have known that modality-specific encoders perform powerful representation learning, and we have also known that audio, video, and MU signals are all related to ALT task to some extent. Therefore, now we combine three modalities together and train the whole system to observe the performance gains. Firstly, let's pay attention to the clean scenario, which means there is no musical accompaniments as perturbations. The combination inputs of audio, video, MU signal can make the system perform the best. In noisy scenarios, we can see that the multimodal system can bring significant improvements, especially in high signal-to-noise ratio environments. About 30% absolute performance gains. Keep looking at the different combinations of modality inputs on different SNR scenarios. We can conclude that MMALT is most robust to perturbations of musical instruments when accepting the input of three modalities. Apart from the quantitative results, here we also show some qualitative results. The extra modalities besides audio signal can indeed help the ALT model make the better predictions. To better understand the key message of our paper, here I show a simple demo to show how our MMALT works. If you want to know more details, please feel free to visit our project website.
My dear, as I lay sleeping, small and white, clean and bright. I wonder how, I wonder why.
Hopefully you enjoy this demo. Thanks for listening. That's all for my presentation.